So hi there. We're going to talk about torque now in this section. This is from chapter 5 in the textbook. It's section 4 in chapter 5. And here in this slide we have some objective and some vocabulary words that we need to know. So we want to be able to explain how torque is created. We want to calculate the torque on an object, and we have a situation where we have something called rotational equilibrium, and that's when we have balanced torques. So some words we need to know, of course, torque itself, rotate, axis of rotation, this thing called lever arm, we'll see that, and rotational equilibrium, which really means balanced torques. So let's get on with it. So you can imagine forces, they cause things to move. Can you imagine a force that causes an object to rotate? Well, this is what a torque is called. Torque is the force that causes objects to rotate. And it's special enough that it gets its own name. So it's called torque. And it's the rotational analogy of force. So a force you could think of being is linear, like you push on a box. So if you push on a box, the box will accelerate and pick up speed, along the floor in a line. But as torque, you can think of some examples would be, opening a door, or starting a lawnmower. You have to pull the cord. That causes the motor to rotate. Or a classic example is turning as a wrench, putting a wrench on a nut and torquing down a nut like on an engine. So let's see an example. I think our first example here is indeed the wrench. So we'll define torque as this funny looking T. This is actually a Greek letter called tau. And torque, and that's equal to the product of a lever arm, which I'll explain in a moment, and a force. Now the force you probably already know, and you have a good concept of what that is. That's just a push or a pull. But in this case, the lever arm is here. We see an example of the wrench. The lever arm in this case is the distance from the force where you apply it to the pivot point, the point that rotates. So if you're going to pull on this wrench downward in the direction of the arrow here, you're going to cause this nut here to spin. So you're going to pull it down. It's going to rotate this way. So we have a force of 100 newtons. And we have a distance here between in this case, the nut and the hand of 25 centimeters. Well, 25 centimeters, that's good, but lever arm, we're going to use meters all the time. And force is going to be in newtons. So this force is already in newtons, but this is in centimeters. So we have to convert this to meters. And this would be 0.25 meters. So the torque in this case would be 0.25 meters times 100, and if you multiply, right here, multiply those two, you get 100 times 0.25, which is 25. Notice the units of torque are Newton meters. Now, some of you might say, Newton meters, that's force times distance, that's a joule, isn't it? And you'd be right, it has the same basic units of a joule, but torque is unique enough, it's special enough that we're going to leave the units in Newton meters so that we can distinguish torque from energy and work. So units of Newton meters. In this example over here, you can see the force is being pulled in the direction of the arm. In this case, we're not going to have any torque. So there's a special condition here that we have to know, and that the radius arm and then the force, the angle between them has to be a right angle. You can see that the angle between the wrench and the direction you apply the force is a right angle, or 90 degrees. And so that's what we need in order to have torque. This one, there is no angle here. It's a 0 degree angle. The radial lever arm here and force are in the same direction, so there's no right angle. So we have no torque. In other words, this force would not cause this nut to spin at all. And I think you can probably conceptualize that. Okay, let's go on to the next slide. So here we have a situation where we have somebody on a seesaw or a bench with a balance point. And this person happens to weigh 3 newtons. That's a force of 3 newtons. That's their weight. And they're sitting a distance of 2 meters from the balance point. And we want to find the torque on this object. Well, here's the force right here, and here's the lever arm. Lever arm is 2 meters, force is 3 newtons. So we can have a torque of 3 newtons times 2 meters, which would give us 6 newton meters. So that's a pretty straightforward example. Over here we have a little more complicated example where we have a weight hanging off of a wheel, and as this weight falls, you can probably see that this wheel is going to spin. Well, we have a lever arm here of 50 centimeters, and we have 1 kilogram here. Now this is a mass, it's not a weight. So we have centimeters and we have mass. So we're going to have to do some unit conversion. So the first thing we need to do is recognize that this is actually a half a meter. 50 centimeters is a half of a meter stick. And this down here, in order to get its weight, we have to multiply by gravity, 9.8 meters per second squared. And once we do that, we get 9.8 newtons. So now that we have our weight in newtons and our lever arm in meters, we can take the product of the two to get the torque. So it's 9.8 newtons times a half a meter, and we get 4.9 newton meters. And here's another example of a door on a hinge. This is a good example to demonstrate and illustrate torque, because the hinge doesn't move, but the door swings on that hinge, in and out. So the question is, how much more or less torque? Well, this was a typo. This was actually, I think I meant to write force. So I'm going to ask two questions. How much more or less force is needed? It's part A. And then how much more or less torque is needed to close the door by pushing it from the center, that's right here at this arrow, as opposed to by the doorknob over here. And you can try this. Go to your door and start off actually right near over here near the hinge. Try and push on the door right over here and close the door. It's actually quite hard. It's very difficult. And as the further over here towards the doorknob you start to push, it should be a lot easier. What's happening there is we're increasing the lever arm, and so we are increasing the torque, which will make the door rotate more. So let's take a look at the force needed, first of all. Well, the torque, this is torque dk, which is doorknob. The torque on the doorknob, if we assume this is some force times some distance, where the distance is from here, the hinge, over to the doorknob, that's R, and the force you apply is F. And if you then apply a torque at the middle of the door, that's halfway over, so that's this R over 2, half of R, which is half of the distance to the doorknob. We're going to have to apply twice the force to get the same torque. And we can see that because in this case we have twice the force. We see 2F here. And notice the 2's will cancel, and we have just left F times R, which is what we had here in this case. So the torques are indeed the same in both places, but the force is greater when you push in the middle, because you only have half of the lever arm. So here's a situation where we have balanced torque. We have two people on a seesaw. And you can probably imagine if this little kid sits way down the end here, and the big kid has to scoot up and sit more towards the middle. So we have, in this case, the little person has a weight of 3 newtons and is sitting 2 meters from the end of the board. And we have a larger person who weighs 6 newtons and is sitting only 1 meter away. So let's take a look at the individual torques produced by each one of these people. So this person, you can see, has a weight of 6 newton times a lever arm of 1 meter. 6 newton times 1 meter is 6 newton meters. Now this little person over here is going to have a torque of 3 newtons times 2 meters, which is also 6 newton meters. And so we have a situation here where the torques are balanced. So these two people on the seesaw would be balanced. That is, the seesaw would not move or rotate one way or the other. So here's a problem situation here where we have some people who want to be on the seesaw. And we have Aaron down the end here who has a weight of 400 newtons. And then here's Olivia at 600 newtons. Now Aaron is sitting 3 meters away from the balance point. Olivia is sitting 2 meters away from the balance point. And we want to know, where does Mauricio need to sit so that everybody remains in balance? And Mauricio has a weight of 800 newtons. Well, let's take a look at Olivia here. We can see that her weight, or force, is 600 newtons times her lever arm of 2 meters. We have 600 times 2, which would be 1200 newton meters. So the torque due to Olivia is 1200 newton meters. And we'll take a look at Aaron. Aaron has a weight of 400, and she's sitting 3 meters away. So we have 400 times 3 newton meters, which would be also 1200 newton meters. So together, both Olivia and Aaron produce a total torque, rotating this board clockwise. That is, this end would come down. This would come down this way, which is the clockwise direction. The total torque of 1200 from Olivia plus 1200 from Aaron is 2400 newton meters total clockwise torque. So we know if we need to balance this, we have to have 2400 newton meters of torque on this side also that is in the counterclockwise direction. So balancing this rotational direction would be an equal torque trying to rotate it the other way. So this end coming down. Well, we know that at 2400, the total torque is going to equal Mauricio's weight, 800, times some distance. So the distance from the center point out. So 800 times what gives us 2400, and I think you can see that what question mark has got to be 3 meters. 800 times 3 is 2400. So we know Mauricio must sit 3 meters from the center here out this way, and that would create a balanced situation. And that's it. So this is the presentation on torque. If you have questions, you can bring them to class. We'll see you later.